Welcome back here to part 2 of chapter 11, chemical bonding. In the first part of this lecture, we talked about different types of bonding. Now we're going to talk about everybody's favorite thing to do, drawing Lewis structures and also molecular geometry. Alright, off to part 2 right now, Lewis structures and molecular geometry. Okay, everybody, it is time for chapter 11, part 2 coming out here. We've been talking about bonding, and in the first part, we talked about different types of bonding, and the two major types of bonding are ionic bonding and covalent bonding. And again, the difference, as we talked about, between these two is ionic bonding always a metal and a non-metal together. And when they come together, as we talked about with those periodic trends, the metals pretty much have all trends that lead to them wanting to give away their electrons, while non-metals pretty much have all those trends that want to gain electrons, keep their electrons. So whenever a metal and non-metal get together, we always have this situation happening. We have a transfer of electrons from the metal to the non-metal. And the result of that is we're going to form some ions. So we're going to form a cation as a result of our metal. We're going to form an anion as a result of our non-metal. And once again, the importance of an ionic bond is that there is no sharing of electrons happening. So we got this complete transfer of electrons, and we get the electrostatic attraction that holds them together. And again, no sharing of electrons. Now, covalent is different. Covalent is two nonmetals together. And once again, because there are two nonmetals together, they basically are at the same sort of location there on the periodic table. They share very similar periodic trends, which means they both really want to hang on to their electrons. They also both really want to sort of gain electrons. So the best that they could do is they decide that they're going to share electrons. So nobody's going to give up their electrons. Nobody's going to fully gain the electrons. So the way that they're able to do that is through sharing of electrons, which is a major difference between an ionic bond and a covalent bond. And as we talked about, that sharing of electrons may be equal, or it may be unequal. And really the overwhelmingly sort of determination of it's equal or unequal. And by the way, when we do have equal sharing of electrons, that is what is referred to as a nonpolar covalent bond. When we have unequal sharing of electrons, that is what is referred to as a polar covalent bond. The overwhelmingly thing that we look at in terms of bond polarity to help us determine whether or not the electrons are going to be shared equally is electronegativity. Remember that electronegativity increases on the periodic table as you go up and to the right, decreases as you go down and to the left. And we could calculate what is sometimes referred to as a change in electronegativity values. Remember, they have values from 0 to 4, 4 being the most electronegative element you can have, 0 being not so much, not really electronegative at all. And if you take the difference in electronegativity values and you hit anywhere from 0 to 0.4, that's considered a nonpolar bond, which means we're going to share the electrons equally. If it is a perfect equal sharing of electrons of 0, for example, it is also sometimes referred to as a pure covalent bond, which is sort of as equal sharing of electrons as you could get. If it's above our 0.4, which is, I guess, 0.5, to below 2, that is considered a nonpolar bond. I'm sorry, try that where I did nonpolar. That is considered a polar bond. It's like nonpolar, but not there. So let's get rid of that there. There we go. So that's considered a polar bond, which again is our unequal sharing of electrons. And the result of that is, again, we end up with something that has sort of a positive side of that bond and a negative side of that bond. And relatively speaking, above 2 is usually ionic. Now, a couple of things that we did talk about when we look at electronegativity, for example,
An example of a covalent bond is F2 that we looked at. This is also a non-polar covalent bond. It's an example of nice equal sharing of electrons, sort of neutral, if you will. That would definitely be a pure covalent bond. We also saw something like HF, I think we looked at. HF also covalently bonded. But here the electrons are going to be shared unequally. And because of that unequal sharing, it creates these partially positive and partially negative charges within that bond that can be represented by those partial positive and partial negative signs, are that dipole arrow that we talked about. And that's used a lot in bonding. And once again, this dipole arrow, which is used for polar bonds, always points to the more negative side of the bond. And once again, the back end that kind of makes like a plus sign back here points to the more positive side of the bond. So here between hydrogen and fluorine on the bottom, hydrogen is less electronegative than fluorine. Remember, fluorine is actually the most electronegative atom that you could have. So it definitely is going to be dragging all those electrons towards the fluorine side. And because it's dragging those electrons towards the fluorine side, that's why we get this buildup of a partially negative charge on the fluorine side of the bond and a partially positive side on the hydrogen side of the bond, because hydrogen is basically losing those electrons. Again, it's important to note that they have not completely lost those electrons. They are still being shared, and that is why they are partially positive and partially negative in terms of their charges. So these are the three sort of types of bonds that we come across. Now, when we talked about electronegativity, a lot of cases you can just use the general trend in electronegativity on the periodic table to help you make a pretty reasonable guess as to whether or not you would have a polar bond in that situation. Definitely, as we saw at the end there, if you're comparing something that's in the same period on the periodic table, two elements, and one is further to the right, then it will probably be a polar bond. Also, if you're comparing two elements in the same group, that's a non-metal, the one further up will be more electronegative and will create a polar bond in that case. Now, remember, there's also a situation where definitely if you are comparing two elements that are the same, like we have here with fluorine, they definitely will be non-polar. But there is that sort of diagonal relationship that we talked about, not directly diagonal, but kind of diagonal and over one on the periodic table, that you could potentially come across two elements that are different but still share the same electronegativity values. I think maybe we looked at nitrogen and chlorine, or carbon and sulfur is another example of that. If you look on the periodic table, again, in that situation, they actually end up having the same electronegativity because one is further up and one is further to the right, though, even though it's lower down, and they sort of cancel out their differences. So most of the time, if you got a couple of nonmetals that are different from each other, they can be a lot of times polar and make a polar bond. But it is possible to have two elements that are different from each other that actually do share the same electronegativity value and still be non-polar. So that's just something to kind of keep in mind. Once again, as we talked about, the electronegativity values would be provided to you if you needed them. Otherwise, you could probably just go by the general trend on the periodic table to figure out, is something going to be polar or not. We also looked at Lewis dot symbols, and again, a Lewis dot symbol is a element symbol and one dot to represent the valence electrons. And remember, the valence electrons are important in bonding because they are the ones that are involved in bonding. So again, if we looked at something like 1s2, 2s2, 2p6, 3s1, the valence electrons are the outermost highest energy level electron. So for sodium, that is its valence electron. On the third energy level, remember, these kind of lower energy electrons are what are referred to as core electrons. They're closer to the nucleus, and because of a lot of those periodic trends, they are held very, very tightly to that nucleus, and they're not involved in bonding. So it's really only these outermost electrons that are involved in bonding, these valence electrons. You could write out the electron configuration, but again, as we talked about, the number of valence electrons will equal the group number, and that is much easier way in terms of figuring out how many valence electrons that you need, group number in terms of the periodic table. So for example, if we did take something like sodium here, I think we looked at, it has one valence electron because it is group 1, 1s2, 2s2, 2p6, 3s1, and we react it with something like, say, chlorine, which is group 7. It will have 7 valence electrons. Remember that there's really kind of no rules per se in terms of Lewis dot symbols, other than you really can't go more than 2 per side. And that 2 per side, if you max out, there is 8 electrons, which is that octet rule that we talked about last time, which is really important. If we do a little electron configuration for this guy, a little 1s2, 2s2, 2p6, 3s2, 3p5, I believe in this case. And what's going to happen in this case is our sodium is going to transfer its electron over to our chlorine. The result of that is at that point, our sodium will then become a positive charge. Our chlorine here will pick up these electrons, or in this case, just one electron, and will become negatively charged. And remember that when you are drawing these sort of Lewis dot symbols for ionic bonding, like we're doing here, you do need to show the charges. A lot of times you put at least one of them in brackets, maybe all of them in brackets, to indicate that those electrons are not being shared in this case. So what we end up with here again is our sodium is going to lose its valence electron, which leaves it at 1s2, 2s2, 2p6. Our chlorine has room for it in the p subshell and going to be able to pick it up right there, which gives it 1s2, 2s2, 2p6, 3s2, and 3p6. That's going to give sodium with a +1 charge the same electron configuration as our friend argon there. No, that's going to be neon. It's like argon, but not so much. It's going to be neon. Argon's going to be over here at 18, which is here. And remember that ultimately, as we talked about last time, the goal of all bonding, both ionic bonding, covalent bonding, is this right here. It is to achieve noble gas configuration. That is basically the purpose of all bonding, is for everybody to end up like our group 8 on the periodic table in terms of their electrons. And that's a really, really stable situation. Now, also remember that the octet rule means that everybody will still make bonds until they get that 8. But our friend hydrogen follows what is sometimes referred to as the duet rule, which means it should only have 2 electrons and never, ever, let me say it 2 more times, ever have more than 2 electrons. And I say that because people, when they start drawing, like to just load up hydrogen with lots of bonds, lots of dots, and that is definitely going to be wrong. So you never, ever want to have more than that. All right, so that was a nice summary, I hope, of what we sort of touched upon there in part 1. Obviously, we also talked about covalent bonding. And remember that covalent bonding, again, is sharing of electrons. So something like H2, when those 2 hydrogens come together, because of the similarity in their periodic trends, they're actually going to share those electrons. And when we're drawing covalent bonding, when using Lewis structures, we can represent those bonding electrons with dots, R lines. So we could draw it like that, R like this. Remember, one line represents a pair of electrons or 2 electrons. We also have double bonds where we have 2 lines representing 4 total electrons or 2 pairs of electrons. And we could have 3 lines, which is a triple bond that's sharing basically 6 total electrons, 3 pairs of electrons. And it is this sharing of electrons and covalent bonding that allows everybody also, again, ultimately to hit there, achieve that noble gas configuration. So in ionic bonding, by losing and gaining electrons, it allows both the metal and the non-metal to end up at that noble gas configuration. when we're dealing with covalent bonding and sharing of electrons that happens when two nonmetals come together, that is going to allow them to achieve noble gas configuration, not through transferring electrons, but actually sharing those electrons. So that sharing part of it is what allows them to, transfer, basically end up at that noble gas configuration. All right, so we left off right here at talking about the steps of drawing Lewis structures for covalent bonding. Now, if you follow these steps that we're going to lay out here and do some examples of, you really should end up with a pretty good Lewis structure when it's all said and done. If you decide to follow some other pattern, if you will, or as people sometimes try to do, and I call it kind of like piecework, where you try to think about, okay, well, nitrogen's got 5 electrons to start with, chlorine has got 7 electrons to sort of start with. How do they all come together? It usually doesn't work really well for people in terms of drawing Lewis structures for covalent bonding. When you kind of do it piecework, you want to think about the electrons in a covalent molecule that you're going to draw as sort of not belonging necessarily to everybody, but you do want to distribute those electrons properly to everybody, and you'll end up with the right structure. So again, try not to go just element by element and atom by atom and how many electrons and where they go when you're doing this. If you follow these steps we're going to talk about, it should really get you to the right structure. All right, so write the skeletal structure for the compound, showing what atoms are bonded to what other elements. So the first thing you want to think about is, how is this sort of compound or structure put together? And there are some rules that help you decide, what element should go in the middle, which one should go on the outside. So in general, the least electronegative atom will occupy the center position. And that is a really good thing to keep in mind. The central atom should always be the least electronegative. Because of that, we should never find hydrogen or fluorine in the center atom. Fluorine should never be in the center atom because it is the most electronegative element you can have. And once again, hydrogen should never be in the center, because if it is in the center and you attach it to a bunch of things, that is way too many bonds to hydrogen. So again, hydrogen can only have 2 electrons, so it should never be in the center, always on the outside. Pretty much hydrogen should look like this, just like that. Or if you're not going to use the line, like this. And that is pretty much what hydrogen should always look like. It should never look like anything else if you want to get it right. So keep that in mind. Now, probably the most important thing that you could do is number 2, and that is count up the total number of valence electrons that are present. And the total number of valence electrons present are really important, because once you figure out how many electrons you should have, you got to have a picture that has exactly that number of electrons. It can't have any more. It can't have any less. It's got to hit that number on the nose. Now, you could be drawing Lewis structures for things like polyatomic ions, which have charges, because remember, polyatomic ions are actually nonmetals that share electrons but have an overall charge overall. And you do have to adjust the electron count. So a reminder that if somebody has a negative charge, that means that we have added electrons to them, and we do need to add it to the total. So a polyatomic ion, we add the number of negative charges to the total. And for a cation, we subtract the number of, and obviously it wouldn't be negative here, a little editing on the fly here. This would be positive here. There we go. We subtract the positive charge from the total here. So whatever the positive charge is, we subtract it there from the total. So you just take that in. Otherwise, you're going to find yourself with too many electrons or not enough electrons if you don't adjust it based on the charge. So logical arrangement, total number of electrons. Then what you should do is you really should just take from the central atom to each of the outside atoms a single covalent bond. Now, personally, I will use lines, so I'm just going to draw that for my bonding, and that's essentially what you want to do. Now, at that point, remember that each line represents 2 electrons. So once you draw the line, or however many single bonds you need, and that's also a really important thing, you do not want to double bond or triple bond right out of the box, which is a common mistake that a lot of people make. They're like, hey, I think it looks more chemistry like, let's just throw in some extra bonds and stuff like that. So you definitely don't want to double bond or triple bond out of the gate. You want to start with single bonds. Each of these lines represents 2 electrons, right? So you want to count up how many electrons you've used, and then all the remaining electrons should go on the outside atoms as pairs of electrons until the outside atoms have 8 electrons. And if you get to a point where you filled up all the outside atoms with these electrons as dots, and you still have electrons that you're supposed to put on your picture, then you're going to go to the center atom and you're going to put them on also as dots. At that point, once you hit the central atom, you should be out of electrons once you've maybe put some on the central atom. At that point, the last thing you want to make sure of is that everybody has met the octet rule. Obviously, except for hydrogen, it should have only 2. And it's at this point that if somebody does not meet the octet rule, that is where you should think about fixing it. And we fix it by making a double bond or a triple bond. So once again, you don't want a double bond or triple bond out of the box. You want to kind of save that to fix a situation where perhaps you did not reach 8 electrons. All right, so that's a lot of rules. If you follow these rules, you should end up with a pretty good structure. Let's see here together how this all works. So we have NF3, which is nitrogen trifluoride. The first thing I'm going to do is figure out the total number of valence electrons. So nitrogen is 5, right, from the periodic table. There are 3 fluorines, and fluorines group 7 from the periodic table. And that's going to give me 21, and 5 is 26 valence electrons. So that number, once again, is a really important number, as that is exactly how many electrons I need when I draw this picture. Now, logical arrangement, I know fluorine is the most electronegative, so that leaves nitrogen should go in the middle. Once again, if you have a situation like this where you have like 1 element and maybe 3 of something else or 4 of something else, most cases that 1 element should probably go in the middle. It's probably the least electronegative, and everything else is directly attached to it. So there's not usually weird arrangements, not all the time. So here we're just going to start with our arrangement. I'm going to put the nitrogen in the middle. I'm going to put my fluorines around. Now, I did put my fluorine there, the third one on the bottom. You could put it on top. It doesn't matter. Once I have the logical arrangement, now I'm ready to actually draw my structure here. So we're going to start with 1 single bond. That's a long single bond. There we go. There we go. To each of the outside atoms from the central atom. At this point, if I count up my lines, that is 2, 4, 6 electrons. So if I kind of subtract that from my total, I have 20 valence electrons that I still need to place on this picture. They're going to go on the outside atoms first in pairs of dots. So we're going to do outside atom here in pairs of dots. So here we go. That's going to be 2. That's going to be 4. That's going to be 6. And that has 8 now around it with the line here and all the way around. So that's 2, 4, 6, 8, 10, 12, and that is full now. 14, 16, and 18 at this point. At this point, I have now placed on this picture 24 total electrons. I still have, by the way, if I subtract the 18 I just put up there, 2 valence electrons to go. Those 2 valence electrons that are left over should now find its way to the center atom, and they also should go on as a pair of electron or dots. I have now distributed all 26 electrons. The last thing I want to do is make sure that everybody has met the octet rule. So let's see if they all met the octet rule. Starting with the fluorine, that is 2, 4, 6, and this guy counts as 8. All the fluorines are the same, so 2, 4, 6, and 8. 2, 4, 6, and 8. And now when we get to our nitrogen, 2, 4, 6, and 8. Everybody has met the octet rule, which means that this is the correct Lewis structure here for NF3. I'm just going to erase that. I'll try to not erase the entire structure here. And one more. Almost got it. Hey, wait, no. Not bad. All right. So again, everybody has 8. We again didn't double bond, triple bond, or anything crazy like that. We just went 1 for 1. Let's take a look at another one here. Now, this is nitric acid, and nitric acid is a molecule that you may not know how it's arranged. So in a situation like this, if it's something I think you can't figure out how it's arranged, or we didn't really sort of talk about it, I would give you some structural information. And in this particular case, it's actually arranged something like this. And the hydrogen is actually attached to one of the oxygens. That's actually what makes it an acid, is that O and H being attached to each other. All right, but we still would follow the similar sort of rules here. We want the total number of valence electrons. So that is 1 for the hydrogen. That's going to be 5 for the nitrogen, and 3 times 6 for the oxygens, which are group 6. That's 18, 19, 24 valence electrons. Again, that number is important because that is where I need to end up. So even though we got a lot going on here, we still will follow the same sort of step, which is 1 single bond to all these guys. And in this particular case, there's actually 2 central atoms. There's the nitrogen. This guy is a central atom, and this guy is also a central atom. There's actually 2 central atoms in this structure. And again, this is the way that it is arranged. At this point, we still are going to follow our normal sort of procedures, which is however many electrons are left, we're going to put on the outside and work our way in. So in this case, we actually made 4 single bonds. So that's 8 electrons. So that means that's a lot of math there. Maybe 16 valence electrons still to go. We're going to start on the outside. Should I put some dots here on hydrogen? I hope you are shaking your head no, because hydrogen is done. It has 2 electrons. So no dots on hydrogen. Don't put anything there. We still have outside oxygen. So 2, 4, 6. Also outside 8, 10, 12. So I've now put 12 more on there. That is 4 valence electrons to go. What is the next outside element? Well, oxygen looks like the next outside element. So we're going to put here 2 and 4. And that is all of the electrons that we need to put on this particular molecule here. And that is a grand total of 24 electrons. So we need to make sure that everybody is okay in terms of the octet rule. So let's take a looky. Hydrogen is done. It's got 2. This oxygen, 2, 4, 6, and 8. So it is good. Oxygen out here, 2, 4, 6, and 8. So it is good. 2, 4, 6, and 8. It is good. When we come down here to nitrogen, 2, 4, and 6. No 8. It is not good. So in this case, we are in a little bit of a situation of not everybody here has met the octet rule, which means we do need to try to do a little bit of fixing. And it is at this point that we need to try to fix that. So you may be thinking, let's fix it. It needs some electrons, right? So let's put some electrons on there and kind of fix the situation. So can I just lay me up a couple of electrons here? Take a moment and think about it. Hopefully your moment is over and you know that you should not do that, because now instead of 24 electrons, I have 26 electrons. No good. Yeah, so you cannot just add electrons. So this is the point where we have distributed all of our electrons, and frankly, we have somebody that has not met the octet rule. So we're going to try to fix that by making a double bond first. And if that should not work, we're going to try to make a triple bond. So where can we double bond? Well, you could double bond to this nitrogen, frankly, in all three locations. The one perhaps is not the best choice is actually this one, because once again, this part of the molecule in this specific case is kind of what makes it an acid. So maybe that might not be the best choice, but you could. So we could double bond to this oxygen or this oxygen. And can I double bond by just putting a double bond in there? Once again, I hope you are looking at your screen and saying not a great idea either, because when I do that, my nitrogen now has 2, 4, 6, 8 electrons, which is good. But my oxygen now has 2, 4, 6, 8, 10 electrons, not so good. And also, once again, we're now back up to 26 electrons, not good either. So when we try to fix these problems by making a double bond and then a triple bond, if the double bond doesn't work, we're actually going to take a pair of electrons and bring them in to make that bond. So for example, I'm going to take these pair of electrons here, and I'm going to actually bring them in to make that double bond. And when I do that, I will end up with a structure that looks something like this. We'll go this way, and now we have a double bond right there. And go this way. And now if we look at it, we are good. We have still here a total of 24 electrons. But what is good is we got 2, 4, 6, 8 for that guy. 2, 4, 6, 8 for the oxygen. 2, 4, 6, 8 for the nitrogen. 2, 4, 6, 8 for the oxygen, and 2 for the hydrogen. Everybody meets the octet rule. Hydrogen has 2 electrons, grand total of only 24 electrons. That would be the proper structure for nitric acid here. Now you may be saying, what happens if I decided not to do this oxygen, but maybe I took some electrons from this? And you could. So if you decided, hey, I want to take these electrons and move them in, you could draw another structure that looks something like this, where your double bond, for example, is over here. And this would then remain a single bond up here. And the rest of it here will remain the same. And that also has 24 electrons. Everybody meets the octet rule. Hydrogen has 2. These structures are related to each other and oftentimes use this arrow that heads in both directions. These are what are known as resonance structures. And resonance structures occur in that situation where you have more than one option that you could make that double bond. And in reality, those double bond electrons, those sort of electrons that are being brought in to make the double bond, are sometimes referred to as being delocalized, which means, frankly, they're moving around. So, for example, if we kind of came back up here to our original guy, those double bond electrons essentially are a sort of oversimplified version of what's going on. If I get something to draw with, would be good. They may be up here at some point, and they may be over here. You know, they're sort of moving around. And that's why one Lewis structure may not adequately describe the bonding situation. The real structure is probably somewhere between them. But because those double bond electrons are delocalized, you could actually, in some cases, draw more than one Lewis structure to describe the bonding that's going on. And when you can basically move the double bond to all the possible positions and draw those Lewis structures, those are what are known as resonance structures. All right, so again, we're following our steps. We're not going to double bond or triple bond to the end to try to fix something, and that should give you the best sort of outcome. All right, so why don't you take a moment here and draw up carbonate and follow those steps and see what you come up with. Let's take a look at this one, see how you did. You should hopefully have a structure, I hope, on your paper. I'm going to start with the total number of valence electrons. So that's carbon, which is group 4, I think. It hasn't moved, I hope. Plus 3 times our oxygens, which are 6. And we do have a -2 charge. So remember, a -2 charge means that it has actually gained 2 electrons. So in addition here, we do have to add 2, and that is for the -2 charge. So that's 18, 20, 24 electrons here is our number. In this case, carbon and oxygen, if we look at the periodic table, looks something like this. Oxygen is further to the right of carbon in the same period, which means carbon is the least electronegative, and it should end up in the middle. So we're going to do our normal sort of everybody around. We're now going to attach with 1 single bond. That has now used 2, 4, 6 electrons. That's going to give us 18 more to go. So on the outside here in pairs, so 2, 4, 6, 8, 10, 12, that's filled up with 8, 14, 16, and 18 in this case. At this point, I have now placed all 24 of my valence electrons. We want to make sure everybody's okay, and I hope when you look at this, you can see all the oxygens are okay. They all have 8, 2, 4, 6, and 8 electrons around them. They're all the same, so they're all identical in that case. But when we look at our carbon here, we're a little short, right? So we got 2, 4, and 6 electrons only. It is short too. So again, we can't add electrons as we just talked about. This is a situation where we can make a double bond to try to fix it. In this particular case, you could actually make a double bond at any of the oxygens. So I am again going to do it from the top. So I'm going to take these electrons once again and move them in to do so. And that will give me a structure here that will look something like this. Little bit of bracket, since it is an ion and it has charges, which is commonly how we draw them. Little brackets on there and the charge on the outside. Now if we look at it, oxygen on the right and left are identical. It's got 2, 4, 6, and 8. 2, 4, 6, and 8. Oxygen up on top, 2, 4, 6, and 8. And carbon now has 2, 4, 6, and 8. Everybody has 8 and meets the octet rule. This is the correct Lewis structure here for carbonate. Now, because in this case we did have the option, as I talked about, that you could make that double bond at any of the oxygens that are present, that means that you could actually draw a few more resonance structures here, or a couple more resonance structures. We could have double bonded to the right there. And if you did the double bond to the right, your structure will look something like this. Double bond action happening over here. Single bond over here. Once again, a little bracket action and a -2. Or we could have double bonded there to the left, which would give us one more resonance structure, which would look something like this. Single bond up on top, single bond to the right, and double bond to the left. Also bracketed up and stuff. So in this case, carbonate actually has 3 resonance structures. You could draw any of these 3 structures. So if the instructions say just draw a Lewis structure for carbonate, there you go. You can pick any one of the 3. They're all perfectly fine. If you're told to draw all of the resonance structures, then you do have to draw all 3 of them. Once again, in this situation, what's happening is those double bond electrons are kind of moving around, And at any point, they may be to the oxygen to the left, oxygen to the right, or oxygen up on top in this case. And the true structure is probably somewhere between all three of these structures. So once again, these are resonance structures. But again, if you were asked, like the question here, to draw a Lewis structure, you could have drew this one. It's okay. You could have drew this one, or you could have drew this one. You did not necessarily have to draw all of them here unless they ask you to draw all the resonance structures. All right, let's try a few more here. Why don't you take some practice? Why don't you draw SH2? Why don't you draw a little CO2? Why don't you do a little N2, a little SO2, and maybe NH4 plus. All right, so take a few moments and draw the Lewis structures for each of these things and see what you come up with. And then we'll take a look at each of them here in just a second. Okay, let's take a look, see how you're doing. We'll start with the first one here, SH2. So sulfur is group 6 plus 2 times 1 for our hydrogens. That's going to be 8 valence electrons. Hydrogen cannot be in the middle, so that leaves us sulfur in the middle. So sulfur, hydrogen's on the outside. Going to do a single bond. That is 2 and 4 electrons. Once again, that's going to give us 4 more to go. Cannot put any more electrons on the hydrogens because they are filled with 2. That means we do need to go to the central atom, and we will put them on as pairs. And that will give us 2, 4, 6, 8 electrons total. And hydrogens each have 2, and the sulfur in the middle has 8. That is a winner, I think, in terms of our structure. Going to CO2, there's 4 for the carbon, 2 times 6 for the oxygens. That is 12, 16 valence electrons. Once again, carbon and oxygen, same period on the periodic table. Oxygen further to the right, which means carbon here should go in the center. We're going to do a oxygen on each side. We're going to do a single bond to this oxygen. That is 4 electrons. That leaves us, if we subtract off there, 12 to go. We can go on the outside here to the oxygen. So 2, 4, 6. That fills up that oxygen. 8, 10, 12. That fills up that oxygen. At this point, we have actually placed all 16 of our valence electrons. Is everybody good? And I hope you see that everybody is not good in this case, and it's actually the carbon that is short. Each of the oxygens are good. Each of the oxygens has got 2, 4, 6, and 8 electrons, but that carbon there actually only has 4 electrons. So to do that, we want to fix it by making a double bond. We could actually double bond either side here. So we're going to take a pair of electrons and bring them in. And that's going to cause a double bond to occur right here. Now, did that fix the situation? And the answer is no. It got better. The carbon in the middle now has 2, 4, 6 electrons, but it is still short. So now you have 2 options. Should you double bond the guy to the right? Should you make a triple bond and go to a triple bond? The answer actually is you should probably exhaust your double bonds first. So because I have the ability to do so, I could also bring a pair of electrons in to do so here. And we will end up with a double bond here. And this would be the proper structure for carbon dioxide, which is actually a double bond in each side, given the carbon, the better structure. Now, what happens if you did want to triple bond one side and you ended up with something like this? I guess it would be something like this. Is this a possible structure? It might be, but it is not as good of a structure as this one. And something that we don't go too much into here, that you will in the next class, you can look at something that's known as formal charge. And formal charge is basically the charge that each element would have if the electrons were fully transferred in covalent bonding. And you can actually calculate the formal charge by taking the number of valence electrons in the element minus the number of non-bonding electrons minus 1/2 the number of bonding electrons. So to calculate the formal charge, for example, here on, you have all these guys here in the structure like this. So if we look at oxygen, for example, here, our oxygen, if we calculate the formal charge, has 6 valence electrons minus the number of non-bonding electrons, which are 2 and 4, minus 1/2 the number of bonding electrons, which I'll just highlight here. There's 2 there, right? And 2 there, that's 4. And if we do that, we will end up with a formal charge of 0. So this oxygen on the right will come out exactly the same. So if you did the exact same calculation, this oxygen over here has a formal charge of 0. This oxygen has a formal charge of 0. If you look at the carbon there in the middle, its formal charge would be 4, which is the number of valence electrons, minus 0, as there's no dots on this guy, minus 1/2 of 8, as it has 2, 4, 6, and 8 electrons. And that also gives us a formal charge of 0. So in this original one that we boxed, which I said was probably the better structure, this guy has a formal charge of 0. This one has a formal charge of 0. And that element has a formal charge of 0. Let's take a look at this structure down here and calculate the formal charge of each of these elements. We did the formal charge here for the carbon. It would be 4 minus 0 minus 1/2 of 8. And that would give us 0. So it does have a 0 here. If we did the single bonded oxygen, which looks like this, that is 6 minus 2, 4, and 6 electrons, minus 1/2 of our bonding, which is 2, will give us a formal charge of 0 minus 1/2 of 2 minus 1, negative 1. And if we did it for the kind of triple bonded oxygen that's in there, the formal charge would be 6 for the oxygen minus 2 for our non-bonding electrons, minus 1/2 of 2, 4, and 6 of our bonding electrons. That's going to give us 6 minus 2, which is 4. And that is going to be minus 3, which is plus 1 in this case. And the key of formal charge, for example, and this is why in certain cases one structure perhaps is better than another. The key of formal charges is the best situation is where you could reduce down all the formal charges to the smallest number. The best situation is you can reduce down the formal charges to all zeros. And that's what we see when we double bond here versus going forth with a triple bond before we double bond. So the take home message here is, in terms of this, there is sort of another reason why it's probably a good idea to exhaust all your double bonds first before you move on to your triple bond. Because in a lot of cases, it will give you a better structure overall, a better structure in terms of something like formal charge, which again, we're not going to talk too much about, but you will see it in the next class that you take. So take home message, try all single bonds first when drawing Lewis structures. If you run into a situation where somebody does not meet the octet rule, then go to double bonds and try to exhaust all the possibility of double bonds. In a lot of cases, it is just one possibility of a double bond. There's not another possibility, but in the case of CO2, there was. Then you should go to triple bond. So single first, then double. Then if there's no more doubles, triple. At that point, by a triple bond, it should be able to fix any problems that you have. All right. So once again, we're not going to worry too much about formal charge here, but again, if you were calculating formal charge, it's the number of valence electrons on the free element minus the number of non-bonding electrons. And those are individual non-bonding electrons minus the half of the number of bonding electrons. So that is, again, one of the things that you sometimes hear in bonding of, what is the better structure based on formal charge. All right, so with that little formal charge detour, let's go back here to our list. And I think we're at nitrogen here. So I'm going to go to the next page so I got a little bit more room to do this. N2, that's going to be 2 times 5, which is 10 valence electrons. And in this case, there really is no central atom. So I'm just going to do my nitrogen sort of side by side. I'm still going to follow the same sort of pattern as to how I've been doing it. I'm going to do 1 single bond. That is 2 electrons, leaves me 8 electrons to go. Going to put them on the outside, 2, 4, 6, and 8. At this point, that's all 10 electrons. I am still short. I'm going to try to make a double bond. So I'm going to take a pair of electrons and bring them in to do so. That's going to give me something that looks like this. Did I fix the problem for my nitrogen on the left? I did not. It went from 4 electrons now to 6. Got better. There is no other place to make a double bond in this situation. So it is off to a triple bond, which works the same way. We got to bring those electrons in. So that's going to give us 1, 2, 3, and we're going to end up with this structure right here. And that would be the proper structure there for N2. And that is how nitrogen gets to a triple bond by having to meet that octet rule. So triple bond is necessary in this particular case. The next one that we have is SO2. I think we have SO2 and NH4+. I think it's the 2 that we got going on there. Yes. All right. So sulfur is 6. Oxygen is 2 times 6. That's 12, 18 valence electrons. Once again, here, sulfur and oxygen are in the same group on the periodic table. Oxygen is further up, which means it's more electronegative. That means sulfur should find itself in the center. We're going to do a single bond. That is 4 electrons, leaving us, if we subtract off here, 14 more to go. Outside first, so 2, 4, 6, 8, 10, 12. At this point, I have put on there 16 electrons. I actually still have 2 more electrons that I need to put on there, and that's going to go to the central atom first as a pair of electrons. And that is how you get those pair of electrons on the central atom in this case. You should not be have laid up some double bonds on both sides, which is a very common mistake that people make. At this point, though, I have now put up my 18 electrons. Is everybody good? And I'm hoping you're telling me no, sulfur is a little short. It has only 6 electrons, not 8. So we do need to make a double bond. In this case, we could double bond either oxygen. I'm going to take a pair of electrons and bring them in to do so. And that's going to give me double bond. Once again, this would be a proper structure here for SO2. I could have double bonded as well this side, but not together, one or the other. And I could have drew a resonance structure, and I'll just draw it underneath, where my double bond is actually to the right. Looks something like this. Also still have the dots on the central atom. Once again, there is no way around it on this particular structure. Those dots need to be there. You cannot double bond both sides and have no dots. So here, dots need to be there on the central atom. That's why it's important to distribute the electrons like we did previously, so that you do end up with those dots. Again, very common drawing for this is I'm just going to double bond everybody. Not a good idea. So again, single bonds, distribute the electrons in dots, in pairs of dots, and then try to fix something if necessary with double bond or triple bond. Last one up here on top, we got 5 for the nitrogen, 4 for the hydrogen, 1 each. And we do have a plus, which means it lost electrons. We do need to subtract in this case. Excuse me. So that's going to be subtracting. That's going to give us 8 valence electrons. We know for sure hydrogen cannot be in the middle. So that's going to give us a hydrogen on the outsides and a nitrogen in the middle. Going to do a single bond to all the outside ones, and that's going to give us 2, 4, 6, 8. Who do we appreciate? That is it. And we're going to do a little box because it's an ion with a charge on the outside. Everybody's good here. Nitrogen has 8. Each hydrogen has 2 proper Lewis structures. So hopefully you can see a pattern here. If you follow those steps, how many total valence electrons should your picture have? Single bond from the center to the outside atoms. All leftover atoms, pairs of dots on the outside until each one has 8. Then if you have any left over, to the center atom, also in dots. And at that point, if somebody doesn't meet the octet rule, that's where you pull out your double bond to try to fix it. And double bond does not fix it, then triple bond. All right, so again, follow those rules. You should hopefully be in good shape. All right, we talked a little bit about resonance here, but we also want to look at bond length, and you do not need to memorize this chart. But if we look at our single bond for carbon-carbon, double bond, and triple bond, the length between two nucleuses, 154, 133, 120, with the carbon-nitrogen single, double, and triple bond, 143, 138, and 116. What we see is our single bond is the largest or longest. When you pop on a double bond, it gets smaller. And if you pop on a triple bond, it gets smaller. So every time you kind of bring electrons in to make a double bond and bring more electrons in to make a triple bond, the distances between the two atoms get closer and closer to each other. So that also relates to how strong a bond is. In terms of bond strength, a triple bond is stronger than a double bond, and that is stronger than a single bond. A double bond's not like twice as strong as a single bond, and a triple bond's not like 3 times as strong, but that's the general pattern. I personally think of it as like you got like a brand new pencil or something like that, big long pencil. You could take that thing and snap it pretty easily. If you take a couple of chemistry exams, you're left with like a little eraser and a nubbin of a pencil left. You try to break that really small pencil, going to be very, very hard to break. And that's sort of how bonds work. As everybody moves closer to each other, the two atoms with all those electrons in the middle, very, very strong attraction as everybody's very, very close to one another, much harder to break. The result of that is it would take a lot more energy, for example, to break a triple bond than it would, say, a double bond, than it would a single bond. Resonance structures, as we sort of touched upon as we were drawing it, so we'll kind of go through this maybe a little bit quicker. Oftentimes represented by this, and we draw resonance structures when one Lewis structure really doesn't represent adequately what's happening. And this is usually the case, as we talked about, where, you know, maybe you have options as to where you could double bond. So maybe you could double bond there, and then in a different situation, you could have brought the double bond over here, and so forth. So resonance structures are, again, multiple Lewis structures that you could draw where you have a situation where your electrons could be double bonded in different locations as they are sort of traveling and delocalized along the bond. Here's some examples that we saw or didn't see. This is ozone, for example. Ozone actually has 2 resonance structures. Could double bond on this side, or you could double bond on this side. By the way, the pluses and the minus are those formal charges we were talking about, and that's actually where those charges are located. Here's our carbonate that we did, and again, those charges are actually carbonate formal charges, and it is -2, and that's actually these 2 single bonded oxygens that make carbonate -2 charge. Is actually, that's where the kind of the negative part of carbonate is on those 2 single bonded oxygens. And that's calculated using that formal charge that we talked about kind of briefly there. Benzene ring, you probably won't see too much of it, and you take organic, you will, but benzene looks something like this. And it is a 6 carbon structure that has 3 double bonds. And by the way, each of these are carbons. These are all carbons. You usually don't draw them in. And it has 3 double bonds. You could draw a resonance structure where those 3 double bonds are on the opposite side. And sometimes you'll even see benzene drawn maybe not in a real organic book, but kind of like that with a little circle. And that indicates that these double bond electrons are delocalized through here. They could be at any of those carbons along the way. All right, so here again, just another example of possible ways you can move the double bonds around and make some different resonance structures. Once again, you do not need to draw the resonance structure unless it asks you specifically to do so. Now, the octet rule is really important, and there are some exceptions to the octet rule. I will say for our class here, everything will obey the octet rule. So everything that you're asked to draw should obey the octet rule. You should not draw any exceptions to the octet rule, but you should know the exceptions, what the 3 exceptions are. When you go to the next class, you will draw a bunch of exceptions to the octet rule, but here we will keep it to following the octet rule. So there are a few exceptions to the octet rule. The first exception is what is sometimes referred to as an incomplete octet. An incomplete octet is pretty much what it sounds like. It is less than 8 electrons. And beryllium, for example, boron, for example, aluminum are examples of things that can have an incomplete octet. For the most part, this is going to be your guy right there that you might see the most in terms of an incomplete octet is boron containing compounds. It is perfectly fine in this case with 6. It does not need 8. It will not need to make a double bond or anything like this. This is what is sometimes referred to as being electron deficient. And later on, maybe 2 classes from now, you'll learn a little bit about that. That is what is sometimes referred to as a Lewis acid, something that likes to accept electrons, sort of electron deficient. So boron, very common, incomplete octet, less than 8 around it. 2 other important exceptions to the octet rule are odd electron molecules. That's really where you have an unpaired electron. So like NO, if you just do the math there, that's 5 and 6. That's 11, I think. And obviously with 11, you can't have paired electrons. Same thing with NO2 as well. These are sometimes also referred to like in atmospheric chemistry as like free radicals, like chlorine does that a lot up there. They're very, very reactive because they have an unpaired electron. That makes them very, very unreactive. Now, the third exception to the octet rule is this guy right here. And out of all 3 of these exceptions to the octet rule, not in this class again, but in further classes, next class that you take, this is going to be the exception to the octet rule that you go with a lot. And this is what's referred to as an expanded octet. There are certain ones that can actually take elements that can take more than 8 electrons, 10 electrons, 12 electrons around them, and be happy with that. And that's the expanded octet. And that is our friend. If you look at the periodic table where sulfur is, and if you go to the right, you go to the left, and you go down kind of in the non-metal region, those are the ones that have the ability to do that. And if you look at the periodic table, sulfur is on period number 3. On period number 3, that is the N equals 3 level. And at the N equals 3 level, if you remember what orbitals are available, that's S, that's P, and that is the first energy level where d orbitals are available. So because they have d orbitals available, they have a place to stash the extra electrons. And those that do not have the d orbitals available cannot do that. And that's why if you look on the periodic table, carbon, nitrogen, oxygen, these are period 2, N equals 2, where there's only S's and P's. These guys can never in that period go above 8. So only sulfur left, right, and down can do that because they have those d orbitals available to them. So like SF6, if I just draw it really quick here, I'm not going to draw all the non-bonding electrons on the fluorines, but if we just look at the sulfur, 2, 4, 6, 8, 10, 12 electrons, and it's perfectly fine. This is also why if you Google things and you draw Lewis structures, you could be drawing something that you shouldn't be. For example, if you drew sulfate, following our rules here in this class, obeying the octet rule, you will end up with this structure, all single bonded. Now, if you Google sulfate, you might see this structure. Where we have our sulfur going above 8 in this case, expanded octet. And if you draw this in this class, it would be wrong because you should be obeying the octet rule in this class. So you should end up with this structure. But oddly enough, the proper structure and the better structure based on formal charge that we talked a little bit about is actually this one. This is actually a better structure in terms of formal charge because it reduces those formal charges on these elements here as opposed to the single structure. But in this class, you should be obeying the octet rule. So you should be drawing the guy on the left, guy on the right's also a good structure and an actually better structure in terms of formal charge going in that expanded octet because it reduces down the formal charge on those elements. So keep that in mind. Draw these things following the rules. Don't Google the things and cheat yourself out of an education as to how to properly draw these things because you may actually be drawing something you shouldn't be. And your teacher, for example, will know that that's how you found it because you shouldn't be drawing something like that. So for this class, you shouldn't be drawing something like this. As you go to the next class, perhaps when you talk about these exceptions to the octet rule and based on formal charge, they may want you to draw it like this. But again, you could end up with two different structures depending on the rules that you follow. So once again, here, everything we would draw in this particular class will obey the octet rule, and you should obey the octet rule, and you should not do the expanded octet either. You should save yourself until the next class to do the expanded octet. All right, let's talk then about geometry and molecular geometry, and this is sort of how the molecules are arranged in three-dimensional space, their sort of structure. Now, molecular geometry refers to the three-dimensional arrangement of atoms and molecules in space. Based on Lewis structures, we can make a pretty good estimate as to what the geometry would be based on really two things. We're going to look at the central atom in most cases. And when we look at the central atom, we're looking at the number of electron pairs and also the number of bonds. And if you look at how many electron pairs and how many bonds there are to the central atom, you could predict the geometry of that molecule based on that alone. Now, the basis of this approach is that it is the valence electrons, and I apologize about all the A's, it should be E's. The valence shell are electrons, and essentially what happens is we have electrons and electrons near each other, which are negatively charged, which means they do not really want to be near each other. So what happens when these electrons get near each other, depending on the type of electrons, bonding electron, non-bonding electron, they will try to get away from each other. And as the electrons start to move, the bonds start to move, and the shape of the molecule starts to change. They cannot escape each other because obviously they're still held on in the bond, but they do try to move as far apart as possible, and that's what gives us our different shapes. This is what is referred to as the valence shell electron pair repulsion model, and once again, it should be an E. That is VSEPR for short, which is probably why they abbreviated that. They're divided into two categories. One where the central atom has no lone pairs. So if you draw the central atom, you'll see no dots, basically. No lone pairs or non-bonding electrons. And ones where there are dots on the central atom. So you'll see dots, basically, in your Lewis structure. Now, there's two considerations when we do geometry, and only when we do geometry, which is really important. And that is if you have a double bond or a triple bond, it counts as a single electron pair and a single bond. So in your structure, if you draw a double bond or a triple bond, when you are counting, it counts as one electron pair and one bond. So that's really important. The other thing that's important there as well is that you can apply this model of geometry to all the resin structures that you draw, and in most cases you will end up with the same sort of geometry when it's all said and done than you have for each resin structure. So for example, when you look at carbonate, all three of those drawings, you'll end up with the same geometry for all three of those resonance structures. All right, so let's take a look at these guys here. Let's start with really the simplest geometry that you can have, and those are our diatomic molecules. And our diatomic molecules are the simplest you could have. It's basically two guys together. The only way you could arrange two things, right, the shortest distance between 2 points, is a straight line. So the geometry is always going to be linear. So when you come across something like F2 that we saw earlier, and you're asked, what is geometry? Geometry is linear. HF, doesn't matter if they're the same elements or different elements, geometry is linear. Oxygen, double bond, doesn't matter, linear. So if you have two atoms only in a diatomic molecule, geometry is always going to be linear. It doesn't matter if they're single bonded, doesn't matter if they're double bonded, triple bonded, doesn't matter if they're the same elements, different elements. If there's only two, shortest distance between 2 points is a straight line, and the geometry will be linear. So now we're going to talk about a couple of things that are important, and this is when we have three or more. If I can find my pen here, there we go. When we have three or more atoms. When you have three or more atoms, the thing that you want to look at always is the central atom. So the central atom is always the most important when you are doing geometry. So here we go. We're going to look at the central atom, which is this guy. We're going to go 1 electron pair, 2 electron pairs. So this has 2 electron pairs. It also has 1 bond and 2 bonds, 2 bonds. Now there's going to be two types of geometry we're going to talk about here. One is referred to as the electron pair geometry name. So this is the electron pair geometry name. And that describes how the electrons are arranged around the central atom, bonding, non-bonding electrons. And we're going to talk about the molecular geometry name, which is also sometimes just referred to as the shape. So the electron pair geometry is based on how many electron pairs there are around the central atom. And in this particular case, with 2 electron pairs, what happens is each of these electron pairs decides we're going to try to get away as far as possible from each other, and they end up being linear from each other, straight line. Now, because they are bonded to these guys, as those electron pairs move, so do those bonds, and the overall shape of this molecule ends up being linear as well. As you can see, 180 degrees is the bond angle from each other. So basically, with only two things apart there in the molecule, 2 bonds, they go as far apart as possible. They end up on opposite sides of each other, and we end up with linear. So 2 electron pairs, 2 bonds. Electron pair geometry name is linear, and so is the molecular geometry name is linear. Let's take a look at the next geometry. Here we have a central atom, and we're going to look at our central atom here, and it has 1 electron pair, 2 electron pairs, 3 electron pairs. It has 1 bond, 2 bonds, and 3 bonds. So once again, the electron pair geometry name is based off of 3 electron pairs. So what happens in this case, because of the extra electron pair, this guy goes this way, this guy goes this way, but then again, these guys can't get too close to each other, and they end up in an arrangement known as trigonal planar, and sometimes people call this triangular. The molecular geometry, our shape of it, is also going to be trigonal planar. They call it trigonal planar or triangular because, frankly, it makes an equilateral triangle. It has a bond angle of 120 degrees, basically. Now, let's take a look at the next arrangement. This is a central atom where we have 4 things attached. And in this case, we take a look at our central atom. Always want to look at the central atom. 1 electron pair, 2 electron pairs, 3 electron pairs, 4 electron pairs. So electron pairs here is 4. Bonds, 1, 2, 3, and 4 bonds. So in this case, our electron pair geometry ends up being what is known as tetrahedral. Most books call it these days. Some books call it tetrahedron. And it also has 4 bonds, which means what happens in this case is this guy goes away, this guy goes away, but now these guys can't get too close to each other either. And it ends up being, in terms of its molecular geometry or its shape, it also ends up being tetrahedral. Has a bond angle of 109.5, kind of like a triangle on the face and almost like a pyramidal type of shape there on the bottom, as you can kind of see here. So 4 electron pairs and 4 bonds, tetrahedral for both the electron pair geometry and the molecular geometry. Up until this point, if we go back and look at our 3 geometries that we looked at, both the electron pair geometry name and the molecular geometry name were both the same in each case. And the reason they were both the same in each case is if you go back and look at the central atom, no dots. No dots, no non-bonding electrons. So because there's no dots and no non-bonding electrons, really, the only type of electrons that we have are bonding electrons, which means as those electron pairs move, so do the actual bonded atoms. So the overall geometry of those electrons in the central atom and the atoms that are bonded to them as they move will end up being the same. Now, when we start to introduce non-bonding electrons, that is where we actually start to see a change in the name of only the molecular geometry will start to change. And that's where we'll start to see a change in the name of the molecular geometry name. The electron pair geometry will still be the same, but the molecular geometry name will actually change. So let's take a look at why that is. And it has to do with the type of electrons that are interacting with one another. And when we have electrons, we basically have 2 types of electrons. We have bonding electrons and we have non-bonding electrons. So we have bonding electrons, which are involved in bonds, and we have non-bonding electrons. So in terms of our Lewis structures, usually bonding electrons are lines and dots, right? Basically for our non-bonding electrons. So the best situation that you could have is where you have bonding electrons near bonding electrons. So they're lines near lines. That's okay. The kind of worst situation, our next kind of worst situation, is where you have non-bonding electrons near bonding electrons. They definitely don't want to be near each other. And really the worst situation that you could have is where you have non-bonding electrons near non-bonding electrons. They really do not want to be near each other, and they do want to get away from each other. Why are they able to get away from each other? They're able to get away from each other a little bit more because they're non-bonding electrons, which means unlike in the bonding situation where you have that extra atom there, in a non-bonding situation, you don't have that atom there. Gives everybody a little bit more room to spread out and get away from each other. And the name that's affected is just the molecular geometry name. So the molecular geometry name or the shape will change when you have non-bonding electrons present. The electron pair geometry name will still be the same. So let's take a look at some of these here. An example of that is sulfur dioxide. And we drew sulfur dioxide not too long ago. Looks something like this. And once again, we're going to focus in on our central atom. And in this case, it has 1 electron pair, 2 electron pairs. And now remember, when we count double bonds, doing geometry, it counts as only 1 electron pair. So in this case, in terms of electron pairs, it actually has 3 electron pairs. The non-bonding electrons on the sulfur, the single bond to the left, and the double bond to the right counts as 1, 3 electron pairs. Now in terms of bonds, this double bond counts as 1 bond. This guy counts as 1 bond. So it has actually only 2 bonds. So what does this mean in terms of our names? The electron pair geometry name, still based off of how many electron pairs there are, which is 3. And that doesn't change. So we saw earlier 3 electron pairs is still trigonal planar. But what happens now, because there is not that extra bond there, but the non-bonding electrons, it gives it a little bit more room to spread out and get away from each other. What's going to happen is these non-bonding electrons are going to go this way. Bonding electrons are going to head this way. And we will actually get a geometry that looks something like this. And our molecular geometry, as they try to spread out a little bit from each other, is going to be what is referred to as angular. Now, some people will call it bent angular. And honestly, some people will just call it bent as well. But we're going to go in this class as angular for this. And it has a bond angle of less than 120 degrees. So the trigonal planar geometry has a bond angle of 120 degrees. This will have a little bit less than because of the lack of that third bond that we don't have here. Going to give everybody a little bit more room to spread out. Another example of that is ammonia. If you draw ammonia, and once again here, if we look at the central atom, it has 1 electron pair, 2 electron pairs, 3 electron pairs, 4 electron pairs. Now, when we're counting electron pairs, always the central atom. And again, it doesn't matter if they're single bonds, lines, doesn't matter if they're dots, double bonds, triple bonds, everything counts as 1. So they could be dots, they could be lines, everybody's going to count as 1 for both electron pairs and bonds. So in this case, in terms of bonds, though, we have 1, 2, and 3. So our electron pair geometry name here is still going to be based off of 4 electron pairs, which is tetrahedral, based on those 4 electron pairs. What happens in this case, same deal. We have our non-bonding electrons is going to go upwards. These bonding guys are going to go down. But once again, they can't get too close because there's that third guy there hanging out. So they kind of try to keep as best of a distance as they can. And they end up with a molecular geometry, I'll just call it MG, of what is known as trigonal pyramid. Has a bond angle of less than 109.5 degrees, like 104-ish in this case. And again, it's because it kind of makes a pyramidal type shape there on the bottom and is trigonal pyramid, also known as trigonal pyramidal as well. Let's talk a little bit about this name and one that we saw earlier. This is trigonal pyramid. And earlier we saw trigonal planar, which is 3 electron pairs and 3 bonds, right? Something different. They are different. And when you give the name, you do need to specify trigonal planar or trigonal pyramid. You do not on an exam just write trigonal and let me choose, because I'm going to choose an X. So make sure that you choose the right one. Don't do the other thing that I also like when people do it. It is trigonal, very confident writing. That looks like trigonal, was it pyramid? I mean, planar, something like that. So don't do any of those things. These are 2 different molecular geometries, and they correspond to different numbers of electron pairs and different bonds. Make sure you choose the right one. And the last geometry that you're going to be responsible for in this class, when you get to your next class, you'll have a lot more geometries to do. Something like water. If we look at water, it has 1 electron pair, 2, 3, and 4 electron pairs. Also has 1 and 2 bonds. Once again, something with 4 electron pairs in terms of electron pair geometry. That is going to be tetrahedral. In this situation, we have kind of like the other situation, the worst possible thing that's going to happen. We have non-bonding electrons near non-bonding electrons. We have bonding electrons near bonding electrons. And we have non-bonding near bonding electrons. So what happens in this case is basically those non-bonding electrons definitely try to get away as far as possible. The bonding electrons also get away as far as possible. And we end up with why we always see water a lot of times drawn in this shape, a molecular geometry of bent or V-shaped. Now, we're going to use bent or V-shaped for this geometry where you have 4 electron pairs and 2 bonds. And again, we're going to use angular for that SO2 type of example. And there is a difference because the bond angle here is less than 109.5 degrees as opposed to for angular less than 120. So this guy's like maybe 104 or something like that as well. Kind of a much smaller than 109.5. So here you can see as you introduce non-bonding electrons to the central atom, what happens is because there's not that extra bond there and you have that worst interaction sort of happening, non-bonding near bonding or non-bonding near non-bonding electrons, they try to get away further from each other as possible. And they're able to do that because of the lack of that extra bond and that non-bonding area. They're able to spread out a little bit more, and that gives us different molecular geometry names and shapes than it does. Our electron pair geometry remains the same based on the electron pairs. Here is a table from your book. You do need to know both of these names. They will not be provided for you. So you do need to know that. And this is really the best way to do it. Kind of number of electron pairs for central atom, number of bonds, and just make a table. We could add the one that's missing here from ours, which would be 3 electron pairs, trigonal planar, and 2 bonds would give us our angular. So we'll add that in there. But that's really the best way to do it. Is most people, myself included, can't really think about what things look like sort of in 3-dimensional space, just to do it based on number of electron pairs, number of bonds, and that's sort of the easiest way to do it. Now, again, remember that double bonds, triple bonds count as both 1 electron pair and 1 bond when you're doing geometry only. And that's an important thing to keep in mind. So let's take a look at maybe some of the ones that we saw previously, or actually that we actually drew. I think we did this guy on that example. I think we did this guy. We did this guy. We did or just did a second ago as well. I think we had this guy. So this is the one I think from the previous example we did earlier. And if we wanted to do the geometry of each of these guys, why don't you take a moment and do both the electron pair geometry and molecular geometry for each of these guys and see what you come up with. Okay, so let's take a look here. So really, this one should be the simplest. Only 2, which is diatomic molecules, which means the geometry is going to be linear. There really is no central atom. And remember that this chart that we're looking at here and that we talked about is really when you have 3 or more atoms. That's where you want to use this chart. All right, so this one we do have 3 or more atoms. If we go to the central atom here, that is 1 electron pair, 2 electron pairs, 3 electron pairs, 4 electron pairs. So that takes us into one of these regions. In terms of bonds, it has 1 and 2 bonds. So that is here. So the electron pair name should be tetrahedral. The molecular geometry name would be bent or V-shaped in this case. We take a look at the next one, which is CO2. Central atom is right there. Remember that double bond counts as only 1 electron pair and 2 electron pairs, which takes us to here. And also in terms of bonds, that counts as 1 bond. This counts as 1 bond. So that has 2 electron pairs and 2 bonds. That is right here. That is going to give us, for this guy, an electron pair geometry name of linear and a molecular geometry name of linear as well. Coming to here, this is the guy we did earlier. In this molecular geometry, it has, again, 1, 2, and 3 electron pairs. Also has 1 and 2 bonds. That's going to be our trigonal planar for electron pair geometry and our angular. Lastly, here, looking at our nitrogen, has 1 electron pair, 2 electron pairs, 3 electron pairs, 4 electron pairs. That's going to bring us to one of these guys. And in terms of bonds, it actually has 4 bonds, which would bring us here. That means that the electron pair name will be tetrahedral. And our molecular geometry name will also be tetrahedral. So this is how you can do your geometry for these things, by looking at the central atom and basically determining how many electron pairs and how many bonds there are. Now you can see in our example here, dots on the central atom, different names. No dots on the central atom, same name. No dots on the central atom, same name. Again, dots on the central atom, different names, right? So different names for something that has dots on the central atom, and again, same name if they have no dots on the central atom. All right, so I want to look at one last thing here in terms of geometry, just to show you. I'm going to kind of erase it and clear it out so we can see. Let's say we had something not like that. Let's say we had something, see that there. Let's say we actually had something like this here. Now, in this particular case, we actually have a molecule kind of like, and actually, let me draw that one as well. Get something to draw that one with. And what I'm talking about is our nitric acid that we drew earlier as well. Okay, so both of these guys actually have 2 central atoms. For the case of the first guy, it's the carbon and the oxygen, and here is the carbon or the nitrogen and the oxygen. When you have a molecule that has more than one central atom, you can actually do geometry for each central atom separately. So for example, for the first one here, we would do it for the carbon. We basically would put our hand over where I just kind of boxed in green there, and we would look at just the carbon here. And the carbon has 4 electron pairs. And this guy does count for the carbon as well. And it has, in terms of bonds, it has 4 bonds, right? So for the carbon, it actually has 4 electron pairs and 4 bonds. The molecular geometry of this guy would be tetrahedral. Now what we would do is we would then go back and look at just the oxygen side as the central atom. So we'll go back now and kind of put our box going this way. And we would still count, though, this line for the oxygen as well, because they are sharing that. So in terms of the oxygen here, it has 1 electron pair, 2 electron pairs, 3 electron pairs, 4 electron pairs. So the oxygen has 4 electron pairs. And it has 1 bond. And once again, this bond would also count for the oxygen, 2 bonds. Which means for the oxygen, its molecular geometry is actually bent or V-shaped, which is what we got down here. So you would do the geometry for each central atom separate from each other by kind of putting your hand over one half of the molecule and then switch it and put it over the other. So we would kind of do the same thing here. We would kind of put our hand to the right, for example, to start with. And when we look at the nitrogen, it has 1 electron pair, double bond counts as 1, and 3 electron pairs, and has 1, 2, 3 bonds. So the molecular geometry for our nitrogen in that case is something with 3 electron pairs and 3 bonds. That's going to give us a trigonal planar geometry. Now we're going to look at the oxygen side. The oxygen has, once again, 1 electron pair, 2 electron pairs, 3 electron pairs, and we still have to count that bond coming into the oxygen from the outside. And that's going to be 4 electron pairs. And it has, in terms of bonds, 1 bond there. And again, counting that guy on the outside coming in, 2 bonds, which means the geometry here, the molecular geometry for the oxygen would also be bent or V-shaped. So if you find yourself with something that you drew has more than one central atom, basically just put your hand over one part of the molecule and look at the central atom by itself. You still count the bonds and the electrons coming in, and then flip it around, put your hand on the other side and count the other central atom. Same thing, still counting the electrons and the bonds coming in. All right, the last thing we're going to talk about is molecular polarity. And do you want to make a distinction between 2 types of polarity that we've been talking about, or that we've talked about before? We have bond polarity. And that is represented with those little bond dipole arrows where it points to a more negative side, a more positive side. And we oftentimes use the difference in electronegativity like we did earlier in the chapter. When we have a dipole moment, this is really talking about molecular polarity. And that is the entire molecule as a whole. Is the entire molecule as a whole sharing electrons equally or unequally? And that's different than bond polarity, where we look at electronegativity and it's just between these 2 atoms in the bond in this molecule, or in this particular bond between these 2 atoms. Are the electrons being shared equally or non-equally? So if you do have a dipole moment, that is usually accompanying a polar molecule, which means overall, when you look at a molecule that is polar, there's a side that's more positive and a side that's more negative. If you do not have a dipole moment, so guys that do not possess a dipole moment, those are non-polar molecules, which essentially means overall the electrons in that molecule are being shared equally. Kind of no charge happening in that particular molecule. There's not a side that's more positive. There's not a side that's more negative. So they are 2 different things. And really the only place where bond polarity and molecular polarity are essentially the same thing is when you're dealing with diatomic molecules. So when you're dealing with diatomic molecules, both the bond polarity and the molecular polarity will be the same. What do I mean by that? Well, for example, if I look at hydrogen, H2, we already know that the difference in electronegativity here, right, in this case, if we look up the values, is 2.1 minus 2.1, which is 0. That tells us that the bond between H and H is a non-polar bond. Now, because in H2, the only bond in the entire molecule is that 1 bond, and because that 1 bond is non-polar, that would mean that this would also be a non-polar molecule. Because frankly, there's just 1 bond present, and that 1 bond's non-polar. You know, same thing if you had a double bond, it has no effect on it. The difference in electronegativity here is going to be 0. And because that is the only bond there, that is both a non-polar bond. And because that's the only bond present, that would make this a non-polar molecule. Now, if you have something like HF, for example, we already know that the difference in electronegativity between these 2 guys, by the way, if you do it, as we saw, I think was 1.9, that is a polar bond where fluorine is more negative, hydrogen is more positive. We could draw our arrow heading in this direction. So this does have a polar bond. And because this is the only bond present, it would also be a polar molecule, where that arrow that I drew up on top would be the dipole moment, right? And also the bond dipole. But in this case, this would be the dipole moment. And it tells us that the fluorine side of that molecule is more negative than the hydrogen side because overall electrons are over there. So the easiest one to determine whether or not a molecule is polar or nonpolar is when you're dealing with diatomic molecules, because they have only one bond present. If that bond is nonpolar, then the molecule will be nonpolar. And if that bond is polar, then the molecule will be polar. Gets a little bit more difficult when you're dealing with 3 or more atoms. And when you're dealing with 3 or more atoms, you need to look at 2 things. First off, is there polar bond? If there are polar bonds, then you need to go to the second thing. And if there are not polar bonds, then the molecule is going to be nonpolar. And if there are polar bonds, yes, then you're going to go to number 2. You have to look at the molecular geometry. So you have to look at that molecular geometry of it. So, for example, if we look at our friend there, carbon dioxide that we saw earlier, between carbon and oxygen, which are in the same period of the periodic table, we know that that's going to create a polar bond with the arrow pointing towards the oxygen being more electronegative. Also, we'll have a polar bond this way. So carbon dioxide does, yes, have polar bonds. So you may think to yourself, all right, well, then it's got to be a polar molecule. But we do need to look at the geometry here. And the geometry, the molecular geometry is, again, 2 electron pairs and 2 bonds, which means the geometry here is linear, basically a straight line. So because of the geometry here, we basically have oxygen pulling this way. We have oxygen pulling this way. And if you can see it, I don't know, but my pen is not really going anywhere because they're pulling in opposite directions. So in this case, because of the geometry, they actually cancel each other out. And this guy is actually a nonpolar molecule. And this is a really good example that you could have polar bonds within a molecule, but because of the geometry that's present, it will actually be a nonpolar molecule. And that is because these bond dipoles that we draw up here, these are vectors. And vectors have direction and have magnitude. Then I fell asleep in physics, but I woke up long enough to know in certain cases, they will cancel each other out. And in certain cases, they will actually add to each other. This is a case that they will cancel each other out. Now, if we take something like water, water also has polar bonds heading towards oxygen in this direction. So it does have polar bonds. The geometry here, as we saw, and again, the molecular geometry here is bent or V-shaped. So in this case, we have basically our polar bonds coming together towards the top. Kind of think of it like a string. You could pull the string up, the entire molecule will move. They actually will add to one another in this case, and we will get a net dipole moment heading in this way, where the oxygen side of water is more positive, hydrogen side is more negative. How does that really work? Well, if you do a little vector adding, you kind of take the vector like this, head to tail, I think. Add the other one to the end of it, and before you know it, they add together, and you get that way. So in terms of the sort of bond dipole arrows, which are really vectors, if you have a situation where they are heading directly at each other in equal and opposite directions, are directly opposite of each other in equal and opposite directions, they will cancel out to each other. Where they don't really head directly at each other in equal and opposite directions, they can add to each other like we see here in water. Frankly speaking, nobody wants to draw vectors and figure it out that way. So there must be an easier way to do it. And the answer is there is. So there are certain geometries which are referred to as being symmetrical geometries. And these are geometries, and these are molecular geometries, by the way, where if we take something in our case here, you guys have trigonal planar. and tetrahedral. And what both of these molecular geometries have in common are no dots on the central atom. They're all bonding electrons. So if you have one of these two molecular geometries on your Lewis structure with no dots, and everything on the outside atoms are the same atoms, it most likely will be a non-polar molecule. They will all be basically equal and opposites of each other, and they will cancel each other out. So for example, if I take something like this, and I'm not going to draw all the dots here, just going to draw really quick. So if I look at the central atom, I have no dots. Everything on the outside is the same. This is going to be a non-polar molecule. That's because we do have polar bonds all heading towards the fluorine, but because they're all equal and opposite of each other in terms of where their location is, you could think of it like a tug of war. Everybody's pulling that string equally and opposite of each other, which means it's not going to go anywhere. They're all going to cancel each other out. So although this does again have polar bonds, because of the geometry here, this will be a non-polar molecule, even though it does have polar bonds. What happens though if I swap out one of those fluorines for a hydrogen in this case? Still have polar bonds heading this way and this way. Carbon and hydrogen is actually a non-polar bond, slightly heading towards carbon, but really non-polar. So what happens in this case though is you got three of these guys, like on the tug of war type of thing, pulling in one direction, and this guy over here is not really pulling in the opposite direction. He's actually pulling a little bit with them. And you're going to kind of think about the whole rope's going to move, the molecule is going to move, if that's like a rope, and it will now become a polar molecule. So that's the exception. So if you have a Lewis structure that you draw that's one of these two geometries, basically no dots on the central atom and everything on the outside is the same element, it will be a non-polar molecule. But if you draw a Lewis structure and you have no dots on the central atom, you have one of these two geometries and everybody on the outside is not the same element. Like we have on the right here, we have a hydrogen and some fluorines on the outside. It most likely will then become a polar molecule. That leaves us the other types of geometries, which are unsymmetrical. And these unsymmetrical geometries, for your cases, is your angular, your trigonal pyramid, your bent, are V-shaped. And once again, these are molecular geometries. What all these have in common is there's dots on the central atom. And if all the outside atoms are the same, then it's going to be a polar molecule. So how does that work? Well, we can look at our water, for example, as an example of that. I see dots on the central atom. These guys are the same, going to be polar. So that's an example of that. So that pretty much leaves you only one thing that you have to worry about, which is the geometry of linear. And because it's a straight line, if you have the polar bonds going in opposite directions or heading right at each other, then it will be a non-polar molecule. But it is possible that you could have in a linear situation, for example, all the polar bonds heading in the same direction. And if that was a linear geometry and they're all heading to the right there, then it would be a polar molecule. So that's something to keep in mind. But since linear is a straight line, it's pretty simple to figure out. This is probably the best way, again, just to go dots or no dots to figure it out. So if we drew up some of the ones that we looked at, previously along the way today. Do a little bit of this. We had this. We have this, I think. We had this. Yeah, we have that. Yeah, we'll take a look at some other ones that we saw along the way too. I think we saw this guy. Good. I think what was that one that we had there? I think that'll work. All right. So why don't you take a moment here and determine are these guys polar or non-polar molecules? So again, we're looking at the molecular polarity here. So take a moment and determine. Okay, let's take a look and see. I had a couple more there at the end. So if you want to take a moment, you can stop and do those as well before we get going. But let's take a look real quick. And this is pretty much as fast as you could do it and probably still get the right answer in most cases, or more than most cases. So here we go. I'm going to look at this one, and this is what I should be thinking. I got diatomic molecule. First off, in terms of polarity, that is a non-polar bond, which means that this molecule is going to be non-polar because that's the only bond present. Here I got three or more. I need to look at the central atom, always the central atom. I see dots. I see these guys are the same. That means polar molecule. I look at the central atom. I got three or more. I see no dots. Everybody on the outside is the same. Based on geometry, this is going to be nonpolar. I look at the central atom. We got three or more atoms, no dots. Everybody on the outside is the same. Going to be nonpolar. I look over here. I see dots. Everybody on the outside is the same. Going to be polar, this molecule. I come here. I see no dots. Everybody on the outside is not the same. And it does have a polar bond going in that direction, which means this is going to be polar in this case. I come here, everybody's the same on the outside. I see no dots. And by the way, this has no polar bonds to begin with because carbon and hydrogen is non-polar. And that means that this is going to be non-polar. Once again, there are polar bonds heading here. And also same thing here. These are polar bonds heading towards the nitrogen in this case. And also, again, polar bonds heading here towards the oxygens and our polar bonds heading towards here. Now, in terms of dipole moment, once again, if you had to sort of draw where the dipole moment would be, in this case, it would be heading towards the chlorine. It would be heading actually towards the nitrogen in this case. With the nitrogen being more electronegative. And this would have none. This would have none. This guy, again, would be heading towards the sulfur, this case. So that's how quick you can determine whether or not a molecule is polar or non-polar. And again, that is molecular polarity, not to be confused with bond polarity, where we look at the difference in electronegativity values. Once again, the only place that bond polarity, differences in electronegativity values, and molecular polarity basically cross over is like the very first example here in a diatomic situation. So they are two different things, and you want to make sure you kind of keep them separate of what we're talking about. So molecular polarity as a whole, is that molecule have equal sharing of electrons? Is there a negative side or a positive side? And obviously bond polarity is specifically talking about between two atoms. Are the electrons going to be shared equally or unequally? And that's what we see here again with our CO2. And that's why the geometry is really important, because if the geometry of the molecule was different in CO2, like it was bent or V-shaped, then it would be a polar molecule. But once again, it is not the geometry. The geometry is linear. And that's why when we do have 3 or more atoms involved, you do have to take that molecular geometry into account. All right, that is part 2 of chapter 11, a little Lewis structure drawing action, some molecular geometry, and some polarity, molecular polarity happening. I hope you've enjoyed part 2 here. We'll see you on the next one. I'm going with maybe the next chapter. We'll talk about whatever that may be. Have a good night, evening, or morning. I'll see you next time. Bye-bye.
Hello, and I hope you've enjoyed this lecture on chemical bonding. Let us finish it like we usually do with a chemistry joke. Let me think of one here. Ah, yes, let's try this one and see how it does. Why didn't the physics and biology teachers get along? They didn't have chemistry.